Hello everyone, welcome to week 9 discussion and thank you for watching our video. And today we're going to talk about interpolation and numerical rule finding. Then after that we're going to give a brief introduction of lab 7. So first, what is interpolation? Interpolation is a technique for adding new data points within a range of a set of known data points, which means we already know some x and y coordinates of some points. However, we don't know the others. So we want to estimate, we want to predict the other points. So you can use the interpolation to fill in missing data, smooth existing data, make predictions, and more. And in MATLAB, we have a very useful function. This function syntax is yi is equal to inter1 x, y, xi method. The inter1 function performs several different kinds of interpolations. So inside the function, we have x and y, and x, y contains the original data, which means we know the x and y coordinates of some known data points. Then xi contains the points at which to integrate, which means we know the x coordinates, but we don't know the y. We want to predict the y coordinate. The method is a string containing the desired method: nearest, linear, spline, and pitched. So we will explain one by one. Nearest. Let's look at the second plot. This one is easier to understand. When we want to estimate the y coordinate of some point, we just need to find the nearest neighbor. Then we use the nearest neighbor's y coordinate to add this point, this predict point's y coordinate. And the linear interpolation is also very straightforward. So let's look at the first picture. And we need to simply connect the point with straight lines to get the prediction of our plot. Then the others are a little bit complex. They are spline and pitched. Let's look at these pictures. And we could see between each 2 points, they are not straight lines anymore. They are curves. So talk about this more. And what's the similarity and what's the difference between these two methods? yi is equal to spline x, y, xi is a syntax. The value of x, yi are determined by cubic spline interpolation of x and y, which means the x, y are the known size of data, and xi are the x coordinates. We want to use spline method to estimate the yi. And yi is equal to pitched x, y, xi means we want to use the shape-preserving piecewise cubic interpolation of x and y. Then this is the similarity of these two methods, which is they both use cubic function, cubic polynomial function to estimate the curves. So between 2 different points, we will draw our curve, and this function could be described by a cubic function. And for different curves, we have different parameters. And how to decide what's the parameter? There's a difference between these 2 methods. So let's look at the first derivative and the second derivative of these 2 methods, and this is the difference between them. The first derivative of spline method, this one, is smooth. However, the first derivative of pitched method, it is continuous, but it's not smooth. So it shows some kinks. So can you see that one, that thing? And also for the second derivative, the spline method is continuous. However, for the pitched method, the second derivative is not continuous. So this is the difference between these 2 methods. And from this comparison, we know than Tiange method. And splitting method is more expensive to set up than the Tiange method. Then, okay, this is everything for interpolation. And next, let's welcome Harry to talk about the numerical root finding.
So we're moving on to the next topic of this discussion, namely numerical root finding methods. This was covered also in the lecture on Wednesday. So the whole point of this is, if you have functions that are perhaps just too complex for an explicit solution method to exist, or perhaps f is given to you, perhaps not as a function, it's just like a black box. Maybe you have a black box you're trying to find the root of. In all of these scenarios, you have to employ these approximation methods to guess, to get a best estimate for what the actual root of a function is. And we're going to talk about two methods in this course and implement them in your assignment. We're going to talk about the bisection method as well as the Newton-Raphson method. So we're going to start off with bisection. The bisection method hinges upon a critical, just mathematical theorem. Basically, the intermediate value theorem, which basically states that if you're given a function f of x that's continuous between two endpoints a and b, and they are of different signs at the endpoints, one's positive, one's negative, for instance, then, because your function is continuous, you know there must exist a point where that function crosses the x-axis, aka a root. The bisection method employs this method, this theorem, to find that root by cutting up that domain between A and B, those initial endpoints, searching through that domain to find that root. So let's see how this works in detail graphically. So we start with the function. This line is the function, okay? We have an initial domain defined by the endpoints A naught and B naught. And we evaluate those points. We evaluate the function at those points, right here and right there. And we first have to check, okay, does f of x have different values, as in the sign, have that different sign at the two endpoints? In this case, yes, that is true. It is negative here and positive there, which implies that there is a root that exists right here. Then we will have to check the midpoint. So we first evaluate the midpoint, we first calculate what the midpoint is. So that's as simple as a naught plus b naught divided by 2. That's m naught. We evaluate the function at m naught and see, is f evaluated at the midpoint here less than a tolerance? If it is less than a tolerance, then you say this point is the root. No need to search anymore because we found the root. Essentially, when f is evaluated at this point, it is so close to 0, it essentially is a root. In this case, though, we say that no, that's not the case because this gap right here, this distance, f evaluated at m naught is not close enough to 0. So we have to check, and now we must now perform iterations to find subsequent points. And we can do that by essentially updating the endpoints. Very similar to your binary search problem that you did in a previous lab assignment, where you look at the signs of the function evaluated at these 3 points, and you say, if the sign of the midpoint, of the function evaluated at the midpoint is equal to the sign of the function evaluated at A, then you update your bounds a certain way. And if this condition is true, you update the bounds another way. Essentially, you're only looking at half of the domain in every iteration. So let's see this in action. In that case, we saw that this is junk. We're not going to look at this side anymore. We're only going to look at this side. And now we've evaluated, we've calculated a new midpoint, M1. And we also have to check, is f valued at M1 with a tolerance? In this case, no, it's still not the case, so we progress more. Find M2, and we say that is close enough. And so we have to establish that f evaluated at M2 is within tolerance, so therefore that is our root. Okay, we return that value. The other method that we can talk about is the Newton-Raphson method. And this is based upon another mathematical theorem, which is basically a linear approximation. Let's actually look at how we can derive this formula next. Okay, so hold on. Let's say that f of x is a smooth and continuous function, okay, and x sub r is an unknown that we're trying to find. This one is a bit different than the bisection method. In the bisection method, we were looking at an initial range. In this method, we are starting with an initial guess. This initial guess, x naught, is a guess of what xr is. So we hopefully say that x naught is close enough to xr. We want to find a x1 that is an improvement on x naught. In other words, we want to find an x1 that is closer to xr than x naught was. We can do this by taking a linear approximation of f of x at x naught and then find the x-intercept of that linear approximation line. So in math, this is what it looks like. We first say that f of x is approximately this. The f evaluated at x naught plus the derivative of f at x naught times a difference in the number line, okay? One way that you can interpret this is, remember that the derivative is rise over run, and x, delta x in this case is a run, okay? Then we set this f of x as 0 because we want to find where this line crosses 0, and then we solve for x1. We solve for x1, comes out here. So essentially we're saying that the next best guess, the next root in this iteration can be found by taking the initial guess and subtracting off this quotient right here. This quotient, let me clarify this to be clear, is this. So that's f of x naught divided by f prime at x naught. Essentially, this is equivalent to a rise times a okay, there we go. It's equivalent to rise times a run over rise. So these two canceling, are left with simply a run, a change in the x-axis, okay? So we're saying that x1 equals the initial x naught minus a delta x, a run, okay? So we're just going to use this over and over and over again to find a better x. So graphically put, we start with the initial guess and evaluate the function at its initial guess. Lo and behold, hey, we should check if the function evaluated at this initial point is within tolerance. We have found a root, no more iterations. In this case, that's not the case. We need more iterations. So if false, we must update x. We must update it to find xi plus 1. So in essence, you just punch in that formula and you find, in this case, x1, okay? And then you evaluate the function at x1, check tolerance. If it is not met, then you keep on moving and keep on updating xi plus 1. So in this case, you find x2. x2, you need to check if x2 is within tolerance. And in this example, I know it's a bit messy, look it up on your own computer screen. x2 is within tolerance. Okay, so we say that f evaluated at x2 is within the tolerance. Done. We have found the root. Now, it should be noted though, this works well when the initial guess is close to xr. We'll see an example why on the next slide. Also, because we're relying on the derivative of f to find the next guess, we need to be aware of vanishing derivatives, namely at points of inflection, at minima and maxima. That's when the derivative equals 0. And you can imagine if you're following that linear approximation at any point to find the next xi, if that derivative is 0 or very close to 0, you might be flying really far left or right, away from actually where x sub r might exist. Okay? So let's take this example right here. Let's say this is your initial guess, x naught right here, and you want to find the root that exists here. You start here though. You take the tangent, follow it down to the x-axis. Okay, that's your next x. Go up to here, evaluate. You take the tangent. You'll get back to here. So on and so forth. You are now trapped in an infinite loop, or at least a very, very inefficient loop. So you should be aware of all of these approximation methods are just algorithms. They're not incredibly smart. You need to be aware of what functions you're actually trying to plot beforehand, okay? So you should be aware of symmetries. You should be aware of where you are putting your guess to begin with, okay? And MATLAB, of course, employs built-in functions to do this for you. It would be terrible if MATLAB didn't do that. MATLAB employs two functions that we're going to use in this class, roots and F0. Roots is specifically used to find the roots of polynomials, only polynomials. So, in essence, the input for this roots are just the coefficients of the polynomial, okay? Placed into an array, and out pop the roots, okay? That being said, it can also find complex roots, if those roots are complex. F0 is a nonlinear solver, okay? It finds the roots for nonlinear functions. That being said, it is important to note that the fun right here, the input function, needs to be a function handle. If you're unclear about what a function handle is, please refer to some of the Wednesday slides. I talked about function handles a bit there. So just be aware that this needs to be a function handle or an anonymous function. More examples. Okay, now we can talk about the lab questions.
Next, we're going to talk about lab 7. And this time we have 4 problems. It's not a lot. So yeah, and the first one is about integration. And the second and third and fourth one about root finding problems. So first, I will talk about the integration problem. And there are 2 parts of this problem. The first part is you are going to create a function that will calculate the parameters and the value of your Lagrange polynomial function. And first, you're going to calculate the parameter of the Lagrange function. And second, you're going to calculate the y value. And the function, it has 3 inputs, x, y, and xx. X and y are the x and y coordinates of some data, some known data. Then the xx is some x coordinates. We want to predict its y coordinates. So the y is the value of your Lagrange polynomial at the given points, and the p is the polynomial coefficients of the Lagrange polynomial. Okay, so this problem is a very common and useful problem, and which means you know some coordinates already, you know the x, y already, and you want to predict the y based on the given points. Okay, then how to do this problem? So record our previous lecture. Solving the coefficients of the models that must be fit to the data is equivalent to solving for the Reynolds coefficients in a system of linear equations. And which means in total we have size of m, x and y. So we have mx and my, and so we want to calculate the Lx is equal to a0 plus a1x plus until an minus 2x power of n minus 2 plus a n minus 1x power of n minus 1. And in this Lagrange polynomial, we have m parameters. We have m coefficients we don't know. And we have m points of x and y coordinates. Then, so what are the constraints for this problem? So if you are giving a data set of x, y points, then what's your equations? What's your linear equations? So for every point, xi and yi, they must be met by this equation, which means if we calculate Lx1, then it must be equal to, we apply the x value to the polynomial function. So the Lx1 will be equal to a0 plus a1x1 until a mn1 times x1 to the power of mn1, and also it works for x2, x3 until xm. Then I hope like you still remember we talked about the trust problem in discussion 7, and we give you several linear equations, and we want to transfer this linear equations to matrix. And this time we're going to do the same thing. We have number m of equations, and we want to transfer them to matrix form. So which means we, like for example, the first equation, then we will multiply this first row by this parameter, and we get y1. So all this matrix, we know the values because we know x1, x2 until xn, and on this right-hand part, we know y1, y2 until yn. So this is everything like we know, but for the parameter, we don't know. We don't know a0, a1 until an, so that's part we want to calculate. So how to calculate this part? How to calculate these unknown coefficients? Then recall our previous knowledge in like our last discussion, and we talk about several different methods like inverse of the matrix times the y, or use pseudo inverse, or use backslash. So you have several ways to calculate the coefficients. This is one method to calculate the problem. And also there is an easier way, which is the building function polyfit, P-O-L-Y-F-I-T, we covered in our last discussion. You can directly use the polyfit to calculate the parameter. However, we really suggest you recommend you to use this way, because by this way it will help you to understand this problem more, and it will help you to do the second part of the problem of the problem 1. So okay, let's talk about the second part. The second part is the comparison between different interpolation methods. And we have, again, we have xy, which has known the xx. Also, we have xx, the row vector of x points. We want to estimate the y point. And we also know the interpolation methods. It is a cell array of char arrays listing which method you're going to compare, and your output will be a figure. And so there are in total 4 methods: and linear, spline, p-chip, and Lagrange. So for linear, you just connect the 2 points and get the estimation. And for spline and p-chip, they are qubit functions. You are going to draw a curve between 2 points and get the prediction, get the curve. And for Lagrange is what we just did in our problem 1.1. So then for each one, for the linear, in this case, you should perform linear interpolation using MATLAB building function inter1 function, which is listed, which is here. There. Yeah, you can see it, right? y is equal to inter1, x, y, xx returns the interpolated value of 1D function at specific points using linear interpolation. And the second one, spin. In this case, you should use building function spin function, which is here. Y is equal to spin x, y, xx. Then for the third method, p-chip, and you're going to use y is equal to p-chip x, y, xx. And for the Lagrange, you directly use your previous function you made in your problem 1.1. And yeah, that's all for problem 1. Then Henry will give an introduction of problem 2, 3, and 4.
So problem 2 is implementing Newton's method, which we talked about. We talked about the algorithm for Newton's method previously in the discussion. We're going to actually implement it now. So let's look at the inputs. We require a function handle to f, the original function we're going to find the root to, and the derivative of f, which is required to find the next x, the next root guess, okay? So those two informations are very crucial. Then we need x naught, which is the initial guess, and a tolerance, because how else are you going to check whether or not the current x guess is the best guess? And then also, looking at some of our discussion after showing you the algorithm, there are perhaps cases where the Newton solver will just go on forever, or at least take forever to obtain an answer. So we want to cap the number of iterations. So we have a max iter. It's a cap on the number of iterations we want you to run. Then out pops the value of the root as estimated by this function, as well as the number of iterations it actually had to run through. Okay? So with this in mind, all you really got to do is just take that algorithm and put it into code form. If you really need assistance for this, I recommend looking at the textbook. There's a really nice section in chapter 16, section 4, that actually has some code already there for you. That being said, be wary of how you implement this algorithm. This can be done very straightforward with iteration, for loop, while loop, or recursion. We want you to, however, choose which way you want to go, but always be wary of how you're going to keep track of how many iterations you have completed so far. Please keep that in mind. You only need to know how to use for, while, or recursion for this problem. Moving on to problem 3 now, bisection method. We're going to implement this now. Looking at the inputs though, makes sense. You just need a function handler for the function, okay? You need a input for the initial interval that you are looking at, tolerance to check whether or not you have found the root, and a max number of iterations. We don't want your code running forever. And you output the root you found, as well as the number of iterations it took to find it. So, very straightforward again. Take that algorithm and put it to code. I advise you to look at the textbook if you have further questions, chapter 16.3 to be specific. Okay? Also, for inspiration, you can also look back at your binary search method. The binary search algorithm you wrote way back when. You do a similar process of updating boundaries that you are going to use here again for these updating steps. Okay? Moving on to problem 3 now. Oh, sorry, problem 2 still has another part. Problem 2, the last part of this question is simply comparing the effectiveness of the two methods that you have coded by yourself with MATLAB built-in functions. Let's just move on and look at how we're actually going to do this. Essentially, you're going to use 4 functions for this problem. You're going to use the MATLAB roots function, you're going to use the MATLAB F0 function, and you're going to play around with your 2 functions too, okay? So roots, you're going to use roots to find the so-called true roots of the polynomial that you're given. You're only going to use this function, you're only going to play around with polynomials in this function, okay, in this problem. So you're going to use roots to find the so-called true roots. Then you're going to use F0. You're going to use F0 to find what it perceives to be the root, given an x naught, an initial guess. And you're going to use roots. You're also going to find another root approximation when you're given an interval as the initial step. Instead of one initial guess, you're given an interval. Okay. Then you're going to run your 2 functions and get the roots back from those 2 functions. When I have these asterisks, though, I mean you have to keep track of the number of iterations that were required to find that root. It's important to note that in F0, one of the outputs that you can specify is called output. And in output, one of the entries is the number of iterations it took. Okay? Look at the documentation in MathWorks if you have any questions. Problem 3. This problem is applying root finding and interpolation to an actual engineering problem. This engineering problem is based in fluid mechanics. Specifically, we're looking at water flowing through pipes. When engineers are trying to analyze water flowing through pipes, They're specifically looking at 3 variables. And we're going to write a function that, when given 2 of these variables, you can find the third for us. And the way that these 3 variables are actually correlated with each other is defined by, or at least illustrated by, a Moody diagram. And these 3 variables are, 1, a friction factor. So some measure of how much energy this water is losing as it goes through this pipe. The second variable is the relative roughness, which is a measure of how rough is your pipe. How rough is your pipe? And then the last variable is the Reynolds number, something called the Reynolds number right here. The Reynolds number is some measure of how turbulent or laminar your flow is. If your water is flowing nice and easy, it's kind of laminar, it's flowing nice and smooth. But if it's flowing really fast or something, it's going to be really turbulent, really chaotic. And we can analyze this Moody diagram in 3 regimes dependent on the value of the Reynolds number. So essentially, what we're going to do with this problem is this. If we give you a Reynolds number, and we give you a relative roughness, can you give us the friction factor? Okay? We can do it like this. So we're going to break it up into 3 regimes. The first regime is when the Reynolds number is less than 2,000. This is a linear function. You need to plug and chug. 64 divided by the Reynolds number, give you the friction factor. Done. Second regime is when the water is very, very turbulent, aka when the Reynolds number is greater than or equal to 4,000. In this case, it's a bit more tricky. You're actually going to have to use root finding. The relationship between the 3 variables in this regime is defined by this function. Okay? Don't be too worried now, because in the end, the only unknown that you will have in this function is f of d, the friction factor. So, move everything to one side, set it to 0, apply root finding, and find the root. The root will be f of d. Okay? So, don't worry too much about that, but you just have to play around with this function here. Okay? Then, the third regime is that transition zone in the middle, within Reynolds number of 2,000 to 4,000. In this range, you're going to have to do some interpolation now. Namely, you're going to use p-chip, as Tiange talked about previously in this discussion, which requires, in this case, you're going to use 4 points to interpolate. Okay, you're going to take 2 points from this range, and you're going to find 2 points from this range, and you're going to use those points to interpolate that behavior in between. Okay, you're going to find the value when Reynolds number equals 1,000 and 2,000, when Reynolds number equals 4,000 and 5,000, and then shove those into p-chip. Okay? In the end, you're supposed to recover something like this. If I were to run this function that you write for all Reynolds numbers along this axis, I can recover basically the trace of Moody diagram for a given relative roughness. Okay? So in essence, what you're saying is, you can see here, that's linear because of the linear function. This part is dictated by that funky log function. And then this is the part you have to interpolate. So you have to take 2 points from here, 2 points from here, and interpolate to get this middle zone right here. Okay? Last function is this. We're taking the Newton method that you wrote. Well, not exactly that you wrote. You're not going to use that function. You're just simply applying Newton's method to more than one dimension. So this is typically 2 dimensions. You're going to use Newton's method to find the roots for a multivariable function. Don't be worried now, because essentially, the math is kind of scary, I suppose, but it looks like this. Okay. The update function, what we had before was x of I plus 1 equals x of I plus that quotient of the derivative by the current function value, something like that. This is the same thing, but now you are playing with more dimensions. You have x of n plus 1 equals the current x minus some quotient. And the quotient is simply this. Remember that the function you're playing with is z. Z equals f in this case, of two variables, x1 and x2. So you can store x1 and x2 in a column vector, x bar, okay? This nabla, this upside down triangle thing, is a thing called a, what's it called? Gradient operator. Thank you. This gradient operator, when you apply it to a multivariable function, essentially gives you this. A column vector showing the partial derivatives. In other words, the derivatives in one direction and the other direction. Okay? And then this blue part right here is simply taking the norm, aka the magnitude of this vector. So when you pry this thing apart, this is how you implement it. You take the guess you have right now at time step n, and then you subtract off this junk. Well, this junk is essentially f evaluated at your current point times the partial derivative in a certain direction evaluated at the current time step divided by the norm. Okay, the norm of the partial derivatives. So I know it looks scary here, but just be aware that you are given a lot of information in this problem. You are going to be given function handles for not only the original f, the big F, but you're also given function handles for the partial derivatives in both directions. So with all that in mind, it's going to be basically a game of plug and chug and careful note paper keeping, making sure you're always looking at the right boards at the right time. And in the end, you're going to plot this, and it's going to look real cool. You're going to use useful functions like surf and plot3 to plot the surface, to plot the z equals 0 plane, and a ring that shows you where the solver is looking at right now. What are the x of n's at a current iteration? And you should see that with subsequent iterations, it will go and go and go until it approaches the actual roots. Okay? So, with that, that is lab 7.